Hi guys, it's Mrs. Seitz. Today what you're going to be learning is you're going to be building upon what you've been learning about triangles, and we're going to be adding some new theorems onto it, as well as building upon what you've learned about your triangle congruence theorems as well. So in this lesson, in lesson 4.6, we have a base angles theorem. And what this says is if two sides of a triangle are congruent, then the opposite angles opposite them are congruent. So for example, if side length AB is congruent to side length AC, then angle B is congruent to angle C. And then we can also say the converse of that as well. So remember flip-flop situation. If you have two angles of the triangle being congruent, so we're starting out with the angles this time, then we can say the sides opposite of them would also be congruent. So we could say that side length AB is congruent to side length or segment AC. All right, and a corollary, remember, is just something that you can automatically kind of prove based on these theorems. If triangle is equilateral, then it is equiangular. And then also a corollary to theorem 4.7, if a triangle is equiangular, then it is equilateral. So equiangular means that all the angles inside are congruent, so therefore all the sides would have to be congruent then. All right, so we're going to use that information to help us with some isosceles triangles. So an isosceles triangle, remember, has to have two side lengths be congruent to one another. So when we look at this, we can see that we have to find the value of y in this situation. We're going to use that base angles theorem to help us to build upon that, to help us to get the answer for y. So let's see what helps us right now in this note taker. So it says in the solution, notice that y represents the measure of a base angle of the other isosceles triangle. From the base angles theorem, the other base angle has to have the same measure. So we know over in this area over here, this angle also has to be equal to y. The vertex angle forms a linear pair with 70 degrees, so its measure is, well, let's look and see where that's at. We're talking about right down here. So since we have a linear pair down here, it has to add up to 180 degrees, so this would have to be equal to 110 down here. So because we know that, and we know that there's 180 degrees total in a triangle, and this is again the triangle that I'm focusing on right here, the one that I'm highlighting here in green. We know that if we add up the 110 plus the two measures of y, it has to equal to 180 degrees. So if I subtract both sides by 110, so I'm going to get 2y is equal to 70. And then if I divide both sides by 2, I'm going to get my answer, which is 35. So the correct answer for this one is going to be 35. All right, so when we take a look at the next one, for the next checkpoint, we want to sort of work on that similar idea with the base angles. You know that base angles are going to be congruent with one another if we know that the side lengths in the isosceles triangle are congruent to one another as well. So to get you started with this one, we know that if the side lengths are congruent, then the angles opposite them also have to be congruent. So we can say, to get you started, that 5x is equal to 75. So when I divide both sides by 5, I'm going to end up with x being equal to 15. So to help me then to get my answer for y, I know that this angle here is 75. I know this angle here sums up to be 75, right? Because 5 times 15 will give me 75. Then if I go by adding up the total to get me 180 degrees, I know 180 is the total, and I know the other two angles are equal to 75. So 75 plus 75 plus the remaining angle, which is 3y, has to be equal to 180, right? So I know 75 and 75 add up to 150. And I'm going to bring down the 3y. I'm going to take off the 150. So that means I'm going to have 30 left over. And that's going to equal to 3y. And then when I divide both sides by 3, I'm going to get my answer for y to be 10. All right, over here on the second problem, you can see there are two isosceles triangles right here in the first one and in the last one. And then if I look inside, I see a triangle that has 3 tick marks of the same length, which means that we have an equilateral triangle. So I'm going to kind of build off of that to help me to work to get these answers. So I'm going to actually get my answer for x first. So right now I know that in this triangle here on the right-hand side, that I have these two side lengths being equal to one another by the base angles theorem. That also means that these base angles have to be congruent with one another. So I know this angle also has to be 70 degrees. So to get my answer for x, I would do x plus 70 and set that equal to 180. So I know 70 and 70 give me 140. So if I do 180 minus 140, I'm going to get x to be 40. So I know my answer for x. Okay, to get my answer for y, it's a little bit different story. So to get that answer, you kind of have to build off of what you know about the top. So let me erase some of the markings that I have and the fact that I know that this is an equilateral triangle in the middle. So I know at the top, I have a linear pair. So I know that this is 70 degrees. I know that inside the equilateral triangle, all the angles have to be the same. So that means I would have to take 180 and divide that by 3. So that means this would have to be equal to 60. So that means the unknown angle right here at the top, to get that information, I'm going to do 180 minus 70 minus 60, and that's going to get me my unknown answer at the top. Now, the reason why I want to know that unknown angle at the top is that actually is going to help me to get my answer for y. All right, so I'm going to do 180 minus 70 minus 60. So the unknown angle at the top is actually equal to 50. So I'm going to fill that in. And again, how I got that is because I know that that's a linear pair. If I add up 50 plus 60, that's 110, and 110 plus 70, that's going to give me 180. So I know that that part here at the top has to be equal to 50. All right, now I can use what I know about the base angles theorem, because if I look, I got an isosceles triangle. So I have the two side lengths being congruent. So therefore, by base angles theorem, I know that these two angles are going to be congruent as well. So they're both going to be equal to y. So I can do y plus y, which is 2y, plus my 50, and I'm going to set that equal to 180. So if I subtract 50 off, I'm going to get 2y is equal to 130, and then 130 divided by 2 is going to give me 65. So the correct answer for y is equal to 65. Okay, now we're officially talking about a triangle congruence theorem that we've learned before in the past. It's the hypotenuse leg congruence theorem, but it falls a little bit nicer into this section because we're talking about some special types of triangles. So since we're talking officially about right triangles and isosceles triangles, this triangle congruence theorem falls a little bit nicely in this section compared to the others. But to remember the hypotenuse leg theorem, if a hypotenuse, which remember is the longest side across from the right angle, and a leg of a right triangle are congruent to the hypotenuse, and a leg of a second right triangle, then the two triangles are congruent. So to fill in the theorem, we have if BC is congruent to EF and AC, so here's your hypotenuse, because it's the side that's across from the right angle, is congruent to DF. Then triangle ABC is congruent to triangle DEF. And remember, the hypotenuse is the longest side, and it's across from the right angle. So important things to remember. Okay, so now we're going to use that hypotenuse leg to help us out with making a proof. All right, so let's take a look at this one. It says the pole holding up one end of a volleyball net is perpendicular to the plane containing the points W, X, Y, and Z. So here they are down here at the bottom. Each of the lines running from the top of the pole X, Y, and Z uses the lengths of rope. Prove the triangle VWX. So where's that one? VWX and triangle VWY and triangle VWZ are congruent. Okay, so we have a bunch of given information. They're telling us that we have some segments being perpendicular to one another, and we also have some segments that are congruent to one another. So I'm betting that we're going to be using hypotenuse leg for this one. So I'm actually going to be writing this one on the next slide to help me for some space. All right. So the first thing we're going to do is we're going to write down the given information. So we're going to do VW is perpendicular to WX. And we know that VW is also perpendicular to WY. And we know that VW is perpendicular to WZ. We also know that VX is congruent to VY. And we also know that that is congruent to VZ. And that's all given. And I'm going to mark up some things on the picture while you guys are filling that in. So we know VZ, VY, and VX. Ooh, look, those are all hypotenuse. All right, and then we also know that we've got a bunch of perpendiculars. All right, this sounds to me like hypotenuse leg. Okay, so what I'm going to say after I've made all that given information is I'm going to build off the part that we have some perpendiculars, right? I'm going to say the angle VWX and angle VWY are right angles. And that's definition of a perpendicular. And so by definition, I can also kind of jump in and say the triangle VWX and triangle VWY are right triangles. And I can say definition of a right triangle. Okay, so the next thing that I can say is based off of that information, I also know that I have a common length. I have this common length of VW in both of them. So by the reflexive property, I can make that statement. So let's go back to the picture and see what I'm talking about. Okay, so we have triangle VWX. So this one in the back, And then we have VWY, they're right triangles. And we also have this common length that they're sharing. So the one that's going up and down, okay? So the one that's starting at the top of the net and coming down, they're common in every single one of those, okay? So by the reflexive property, they're going to be the same. Okay, so we've got that one. So I can then say by hypotenuse leg, and I'm just going to abbreviate that as by HL, I can say that triangle VWX is congruent to triangle VWY. And I also can say with similar reasoning that triangle VWY is congruent to triangle VWZ. So we can say by that reasoning, and I'll actually make that a second or a separate step to say that by all of these, that this would be through the transitive property of congruence. That we can say that each one of those triangles would in fact be congruent with one another, because you can cut that middleman out right here of this VWY so that every single one of those would in fact be congruent to one another. All right, the last thing of today's lesson is we are going to take a look and we are going to do one last proof. So we're going to be given the fact that RV is congruent to ST and it's already marked on us, and also that RTV and SVT are right angles. So again, that's already marked in our picture. We want to prove that RTV or triangle RTV is congruent to triangle SVT. So to set up our two-column proof, remember always state your givens first. So segment RV is congruent to segment ST, and angle RTV and angle SVT are right angles. And that's a given. Okay, so the next thing I'm going to do, I'm going to go right off of that fact that I have right angles. I'm going to say that angle RTV is congruent to angle SVT because I know all right angles are congruent. Okay, the next thing that I'm trying to see, I see a matching side length. So down here at the bottom, look here, we got TV in both of those. Okay, so what I'm going to say next is I have TV congruent to TV in both of those triangles. So if you're looking, I have a leg, I have a right triangle, I have a hypotenuse, right? So since I have a hypotenuse and I have a leg now, then that means I'm going to be using hypotenuse leg to prove that these triangles are congruent. Before I can do that, though, I'm going to use reflexive property. So I got my leg in green. I already had the hypotenuse given to me. So I'm going to say triangle RTV is congruent to triangle SVT, and that is by hypotenuse leg. All right. So guys, for today, the important things out of today's lesson, do you know what the hypotenuse leg theorem is? So if you're given the hypotenuse, which is, remember, the side that's across from the right angle, and a leg on two triangles that are corresponding with one another, then you can say that those two triangles are congruent. The other important idea from today's lesson is with the isosceles triangles. So remember, the triangles that have two side lengths that are congruent. If you have two side lengths that are congruent, then you can say that the angles opposite from one another in the base angles are also congruent to one another. And you can also go off of those to come up with the converse of the base angles. So you can say if angles are congruent, the opposite sides are going to be congruent. And then you can build off of that to get some equilateral relationships and equiangular relationships as well.